All right, everyone, it's time to go over our last question that we're going to cover together in this year's AP questions. So part A says, based on the design of the study, would a statistically significant result allow the medical center to conclude that the new procedure causes a reduction in recovery time compared to the standard procedure for patients similar to those in the study? Explain your answer. Now again, I'm going at this looking at it fresh without looking at the scoring guideline before I go over it. Trust me in that. I'm trying to keep it as real for myself as it is for you. The difference between you and I is that I'm not really actively looking at notes. Again, please be studying on your own in between these videos and assignments. But my answer to this question, and we'll see if I'm right in a second, would be yes. And here is my reasoning. They did an experiment where we had patients who were randomly assigned 2 different treatments, and the essentially control group being the standard procedure and the experimental group being the new procedure. So because we randomized, because we're assigning treatments, and because we're only seeking to conclude to those similar to those in the study, I do believe we could make a causal argument that the new procedure would explain the recovery time. Essentially, the idea is you've done an experiment. If you're doing an experiment, you should be allowed to, if you've experimented correctly and obtained your samples correctly, you should be able to conclude causal arguments to your sample of interest. So 4, yes, it would be reasonable to people similar to the study. They were randomly assigned to 2 procedures, which reduces confounding variables. Therefore, okay, and let's see the real breakdown of that. So there's always the scoring. So do you correctly state that it is reasonable? Do you justify that based on random assignment? And do you include context of the situation? So again, you always want to, in this word problem, readdress the fact that you're talking about ACL surgery and other things like that. Now again, the random assignment or the fact that you're doing a randomized experiment, that's what is really allowing this to be causal. So the answer is yes. Why is it yes? Because you did a randomized experiment. So you can conclude to a similar population of your sample. And of course, include the context of what you were doing. We were talking about ACL surgery and mean recovery times. And you can see partial arguments here if you need to, right? Again, my other big thing I haven't mentioned so far, lean on the side of being more critical on yourself than less critical. If you're sitting there going, well, I think I said that, honestly, assume you didn't and try to learn from it. That way you're just gonna have the most opportunity to improve on really answering your questions well. Okay, so part 2, we still got a lot of time left, and that's because this is actually, it's, I guess, the second half of the question, but it's going to be the longer half of the question. So now we're given the data of the experiment that they ran. You can see the 210 that they were talking about. We can see, an immediate difference in the mean recovery time, but this means nothing until you form a full hypothesis test. That's how you find statistical evidence. So we've got a lot to do in this question. Here it goes. First, what I'm going to do is define my variables. I'm going to let mu of S be the population mean recovery time for the standard procedure for surgical ACL repair. All right, really make sure that you're defining that carefully. And then I'm going to let mu of n be the analogous recovery time for the new procedure. Now again, I'm not sure if I should actually copy everything word for word, but I think this gets the idea across. Now again, you have to define your variables before you write a hypothesis test, because we do want to test to see if the new recovery time is quicker. That means it should be less. But before we write HO and HA, we need to define what we're going to call mu of S and mu of N. You might use mu1 and mu2. That's fine, but just make sure you clearly define what they mean to you. Don't let the reader assume that you know what they mean. Prove to them that you know what you're doing. So I'm going to write it like this. I'm going to say that the mean for the new time should be less than the mean for the standard time. Now my HA, I'm going to say, HO is always equal to. So we're going to assume that they're similar, but we're trying to say alternatively, hopefully, the new procedure has a smaller recovery time, a faster recovery time. Faster means smaller in terms of time. So there we go. Now, other ways you could write this is mu of n minus u of s equals 0. You could just move this to the other side and now it would be solved for 0. But both of these are technically correct. So we have our definitions, we have our hypotheses, and we are going to do a t-test for 2 sample difference. I can't spell today. Two sample difference of means. All right. So we have our sample of standard, our sample of new. Those are our two different samples. And we are going to test the difference between their means. So we want to see how different are they. Are they almost similar, or are they significantly different where we want the direction that the new treatment is less than the old? So we have to name the test. Now after that we have to show we've satisfied the conditions of the test. So each sample size is greater than 30. So our sample distributions are going to be approximately normal. That's one. We did obtain samples randomly. And we can assume our population is at least, our populations are, I should say, because we have two populations here. Well, actually, no, we could say population is at least 10 times larger than our sample size. All right, any test you do, pretty much, you always have to sample randomly. We always need to ensure that our populations are approximately normal so that we can use the Z or T table. And we also want to assume that our population is at least 10 times larger. In other words, that our sample size is 10% or less than the population of interest. Okay, from there we can start to do things a little bit more quickly. Now one thing you might want to do is you might want to actually write out the test. So since we're doing a test for the mean difference and we're doing a t-test, what we're going to do is we're going to form our t-statistic, which is going to be our sample means that we got, which, and again, we're going to do this in the order of n minus s. So we're going to essentially move this over and solve this for 0. So the n recovery time is 186, minus the s recovery time is 217, and that's minus the expected 0. Again, we're assuming that there is no difference at first until we prove otherwise, so we'll take our point estimated difference and subtract it from 0, and we'll divide it by, we have this formula for standard deviation, which is standard deviation 1, or standard deviation from new, squared over its sample size, plus standard deviation 2, squared over its sample size. And you can plug that into the calculator and figure it out. Let's see here. So we have to do this carefully. 186 minus 217. I'm not going to write minus 0 because technically you don't have to. Divided by 29 squared over 100 plus 34 squared over 110. And I get a t-value of negative 7.127. Negative 7.127. Now this is our test statistic. And I'll say with associated p-value of, and this is where I'm going to run to my calculator to just actually do the full test. So stat, tests, we're doing a 2-sample t-test, and we're going to input our data in stats, not data. We only have a summary of the statistics, not the actual data. So I'm going to make one. One should be in the order of your hypotheses, so I'll make one the new. So again, the new mean sample was 186. The standard deviation was 29, and the sample size was 100. For the second one, it was 217, 34, and 110, and we're testing that the second is greater, or in other words, that the first is less than the second. Pooled should always be selected for no in this class, and now I press calculate. Again, you can see the t-value that I got. I just showed the work for it, and there actually is a reason that I did that. And this p-value essentially means incredibly small. It means that there should be a decimal place with 11 zeros and then the 8 is next. Or in other words, you should be moving this decimal place to the left 12 times. So what I'm going to say is with associated p-value less than 0.0001. I mean, I'm just showing that it's very small. Now, one thing you might want to do is you might want to show that you obtained this result in the calculator. But again, this output tells you the test statistic and the value of the p-value. And just to review how you can find that p-value by hand, let's go to our reference sheet here. I mean, number one, we can stop here and see that this is where I was forming my standard deviation. And this is the fact that I was comparing the mean 1 from mean 2 by using the sample means, things like that. Now, this is a t-test. So once I find the t-value of 7, I need to go to my closest degrees of freedom, which we should be using essentially this 100 right here. And again, you can see that 7 is totally off the page for our associated degrees of freedom. So since 7 is off the page, you can really say, well, the last thing I know is that it's smaller than, because you can see these are getting smaller. So if we're trying to get to 7, we need to go further to the right. We would be smaller than 0.0005. So again, we know exactly what it is with the calculator, but you can also estimate it like that from the table. Okay, so last thing I'm just going to verbally say, I've been talking through a lot of this, hopefully you've been following, just want to finish somewhat on time, is since, well, you know what, I'm just going to write it out anyways. And I'll speed the video up. But you can see that I kind of would have finished within the time period. Since the p-value is smaller than, let me see if they actually gave me the exact alpha they wanted, then I guess I'll say it like this. Since the p-value is smaller than any standard value of alpha, either 0.05 or sometimes we do alpha equals 0.01, we can conclude there is statistical evidence that the new procedure results in faster recovery times than the old procedure for ACL repair, or maybe torn ACL repair. Okay, so again, I'm a little over in my time. You can see currently I'm at 17 minutes, but I was definitely talking through, not working through it in the fastest fashion. But hopefully you see that this problem has a lot to it in the second half. Let's quickly look at the scoring guideline and see all that we had to do. You can see why I went through so many hoops here. Section 2, we have to define our parameters correctly. Now that's where I was defining the U sub S and U sub N. You have to have the hypothesis imply equality in the null and the correct direction in the alternative. You have to correctly identify the test by name or formula. So you can either say it right here or simply write out the formula here. Both of those are valid. And then you have to have the correct value of the test statistic calculated correctly. So the negative 7.127. Make sure that is what they got. So yeah, approximately 7.13. Okay. After that, that's kind of the first part, that's section 2. Then there's section 3. Do you have an approximately correct p-value that is consistent with the test statistic? Do you justify that your conclusion is based on the p-value compared to alpha? And did you correctly state the conclusion in context? So this one says there's no alpha level needed. You just have to show that the p-value is super small. And there's a lot of other nitpicky things you can read in here, but if we just look at their answer again, they defined U of S and U of N. They showed that U of S should be larger than the new procedure. Notice I wrote mine the other way, but that's actually totally appropriate. It doesn't matter which way you write it. Again, it's an experiment. They were randomly assigned. We can assume they're normally distributed because their sample sizes are large. Again, they found the correct test statistic, and they found the p-value, which was very, very small. Because the p-value is very small, we can conclude that for patients similar in the study, the new procedure would have a smaller recovery time than the new. Goodness. All right, a lot of questions. Just took some extra time to cover what was going on at the end. Best of luck. Hopefully you learned a lot. Again, whenever you read the statement, is there enough statistical evidence? This is how much work you should expect to do. So it's the whole hypothesis test from start